Arduino is an open-source microcontroller-based development kit created by an Italian company of the same name. An urban legend has it it's got its name after a bar somewhere in Italy where some of the project founders used to hang out. So today, we're going to find out why Arduino is so popular and why it's gained such recognition among amateur electronics enthusiasts around the world. This is Mattino. First, let us define the term microcontroller. A microcontroller, also abbreviated to MCU, is basically a tiny computer packed into a single integrated circuit. Most people probably have an idea of what major parts of a computer are. A computer has a central processing unit, CPU, responsible for calculations, memory used to store programs, data and results of calculations, and input-output ports used to communicate with the user. A microcontroller is a device that contains all these components in a single package. But unlike a personal computer or a smartphone, is not designed to interact with a human. Instead, it is intended to automate devices. The processing power of a microcontroller is much lower than that of your regular smartphone's processor, for example, because it's not intended to compute 3D models in real time or play back 4K videos. Also, a microcontroller typically does not have its own operating system and is not able to run user-installed software. The program that a microcontroller runs is written by the developer of the device it's installed in and is hard-coded into its memory. Such programs are traditionally called firmware. Microcontroller-driven devices can be found everywhere. Those include microwave ovens, washing machines, fridges, TV remotes, laptop smart chargers, traffic light control units, etc. Microcontrollers are used to drive car engine ignition and fuel injection. They are installed in car alarm systems, home electric gates, door intercoms, and so on. So, we can conclude that a microcontroller is a fully independent device capable of automating domestic and industrial processes. So, what is the goal of Arduino then? Arduino is an open-source software and hardware platform, a convenient learning environment aimed to help you learn to code microcontrollers and build microcontroller-based devices. But what's so special about that? Did microcontrollers exist long before Arduino was introduced? And the answer is yes, they did. The area was pioneered by Texas Instruments and Intel, who started manufacturing MCUs back in the mid-70s of the last century. Later, they were followed by Atmel and Microchip. But beginners like me and you were strongly discouraged from using them. In the first place, because you cannot debug microcontroller firmware on your desktop computer. Yes, you can emulate the code, but you have no ways of seeing how it's going to run on the actual device, especially if the code is time-critical. So you're basically limited to simplistic code expected to run from the box. Driving any complex external components like an LED display or a stepper motor or a serial ROM wasn't something a beginner developer could easily pull off. So basically, using microcontrollers was a privilege of large companies who could afford, back then quite expensive, emulation hardware that allowed to run and debug the code within the embedded system, or as they say, in circuit. Arduino's approach, on the other hand, was quite revolutionary. First, the microcontroller was supplied already soldered into the board, which took care of powering the MCU and programming the flash memory. Second, the board was equipped with standard DuPont pin headers that allowed connection of external boards. In Arduino, they are called shields. Third, the development software, also called the IDE, was open source and could be downloaded for free. Fourth, You didn't have to unplug the MCU to flash it. A technique called bootloader was used instead. Essentially, a bootloader is a tiny program hard-coded into microcontroller's memory that is used for flashing the ROM. It is still necessary to use a ROM programmer to flash the bootloader into the chip, but it needs to be done only once. And on all Arduino boards you may purchase, it has already been done. Whenever a developer intends to upload firmware onto the MCU, the bootloader takes over. It receives the data dump from Arduino IDE and flashes it onto the microcontroller. No external programmer is necessary to carry out this task. Arduino boards sold today are based on Atmel family microcontrollers. They are connected to a personal computer with a USB cable, which is used both to program and power the device. So all you need to get started with Arduino is a regular Windows computer with a spare USB port, an Arduino board, a USB cable, and a piece of software, the Arduino IDE, which you can freely download off the Arduino.cc website. Arduino produces several board models. Basically, they differ in memory size, performance, pin count of data exchange headers, and, naturally, physical dimensions. Although different Arduino boards are based on different MCUs, the Arduino IDE is compatible with all of them. Programming is basically transparent to the end user no matter the MCU core. So, in theory, any Arduino program you may find online, which is by the way called a sketch in Arduino universe, is pretty much compatible with all Arduino boards, or can be easily adapted, except when the sketch contains something really specific to a certain board model. Millions of enthusiast programmers like me and you create new sketches every day, which makes Arduino the most popular amateur hardware and software platform on the planet. Just to mind you, because different Arduino boards still use different MCUs, if you've plugged in a new board into your USB port, you must specify this in the IDE settings. So, if trying to upload a sketch, you see an error message, the first thing to check is Arduino board type specified in the IDE settings screen. Another thing you have to pay attention to is setting the COM port number on the very first run of the IDE. Ironically, Arduino does not have a COM port, because, like I said, the board uses a USB connection. If you haven't been using computers in the 90s, you probably have a really vague idea of what a COM port is. Its connector looked like this. Back then, the COM port was about the only standard way of attaching external devices to your computer. You could say that in a way, it acted in place of a USB port before it came around. Using a COM port, you could connect mice, modems, plotters, tablets, and all types of external gear to your system. The COM port should have been obsolete by now. But because a huge amount of software had been written for the COM port in the previous years, many devices and software packages still use it. Not the physical connection, but the protocol itself, the signaling, and it's called virtual COM port. For that purpose, modern devices employ USB to COM emulation. As opposed to a hardware port, an emulated COM does not have a fixed address, so it will change every time you move the USB cable from one socket to another. That means to be able to use an Arduino board with the Arduino IDE, you must specify your virtual COM port address in its settings, especially if your system has other devices utilizing a COM port emulator, or if you have several Arduino boards attached to your system. Here I would like to point out one important consideration purchasing an Arduino board. Because Arduino is based on open source concept, it was always intended to be cloned, ideally for no profit. In reality, that means most boards sold online are not original Arduinos. Chinese clones are much cheaper than Italian originals, but may be inferior in quality. There's also an issue with COM port emulation on Chinese boards. If we examine a better versus cheaper copy of the Uno, we can see the chips next to the USB port are different. A cheaper clone uses the Chinese-developed CH340G USB-to-COM converter, while the original uses the ATMEGA 16U2 microcontroller. So what's the actual difference? The 16U2 has a much versatile functionality. Although initially it is programmed to emulate the COM port, just like the CH340, if you use a specific set of instructions in your sketch, you can reprogram it, for example, to act as a USB slave device. It will be able then to emulate a USB mouse, a USB joystick, a scanner, a touchscreen, etc., which is something the CH340 is not capable of, since it's just your plain USB-to-COM converter. It's quite possible, however, that it will suffice for most people. But apparently, the limited CH340 functionality is not its only problem. If you encounter intermittent problems downloading sketches to the board, if you have to replug and re-upload to succeed, the culprit might be the CH340. In my experience, the CH340 worked promptly with 50cm cables only. That's the reason why Chinese sellers often bundle their boards with them. Needless to say, I would not recommend to use a CH340-based boards to drive a 3D printer either, because its functionality is based on transferring data via COM port. It's not quite clear what the problem with the CH340 is. It could be poor manufacturer quality or developer errors, but I've personally made up my mind to never purchase and use the CH340-based Arduinos. However, in some cases, you could benefit from the CH340 as well. For example, if your code is fully debugged and does not use communications port, such sketches will run on the CH340 smoothly. And especially if you're up to purchasing some boards in bulk to program them and sell as end-user devices, there's absolutely no point to pay extra for the 16U2. In that case, however, you could consider dropping the Arduino altogether and creating your own board design using the same Atmel MCU. That'll be even cheaper. But if your goal is to learn programming using Arduino, you should absolutely get the 16U2 board. For your convenience, I will leave the links to purchase both versions of the boards in the description. Let us take a look at the Arduino Uno schematics. As Arduino is open source, all specifications are available online. The MCU is the ATMEGA 328P. Here it is on the right. Any particular CPU basically needs two things to function: the reset signal and the clock pulse. The reset is pin number 1. As we can see, it's active low. So to restart the CPU, we have to pull it to the ground. The pin is connected to the reset button, bootloader programming header, the power connector, and also the 16U2 microcontroller, responsible for downloading sketches. We do not, however, see here the classic reset signal circuit that would pulse the pin low. That is because the ATMEGA 328 has an internal reset circuitry that takes care of resetting the CPU. We also have a 16 MHz crystal wired between pins 9 and 10 that allows the internal clock to run. The processor is powered by 5 volts, which is applied to both pins VCC and AVCC. The VCC powers the CPU logic, while AVCC is used to supply power to analog to digital converters. These power lines are separated on the chip to make sure no interference or crosstalk happens between digital and analog parts of the IC, and ideally should be fed power separately, but in Arduino they are joined for simplicity. On the right, we can see the data ports of the processor. They are grouped into B, C, and D 8-bit channels. The B and C on this particular MCU contain only 6 bits each. Port D contains 8 bits, and port A is absent. This is due to the fact that the ATMEGA 328 has, obviously, only 28 pins, and is, so to speak, a younger brother to the family of microcontrollers that have larger body packages and full-sized 8-bit ports. And here's something important you must know about Arduino ports. The developers, probably for the sake of board-to-board compatibility and simplicity, decided to drop the internal MCU port numbering and assigned their own numbers, I would call them virtual, to all input-output pins. These numbers are in no way associated either with physical MCU pin number or programmatic MCU port number or address. And that's something you're going to deal with throughout your whole Arduino experience. In case of the Uno board, digital lines are numbered from 0 to 13, and analog lines from 0 to 5. The reason they're organized exactly like that is due to the fact that internally the analog to digital converter is connected to port C, and that's where A0 to A5 lines are attached. The designations on the Arduino boards also use these virtual pin numbers, and those are the ones that you are going to use when creating your sketches. Once again, please note, they do not coincide with physical MCU pin numbers or port bits. Please keep that in mind when reading schematics for someone's projects you may have found online. All Arduino digital and analog pins can be used either as inputs or outputs. This, of course, is in no way the merit of Arduino, but the functionality of the ATMEGA 328. The Arduino IDE provides a convenient and flexible way of configuring them in your sketches. Let us give it a try and write our very first program that will use the Arduino digital output. The Uno board has a test LED, which is hardwired to pin 13. So now we're going to try to turn it on. By default, every Arduino sketch has a standard structure that contains two basic procedures. One is called setup, the other one is called loop. The setup procedure is only executed once on startup or reset of the board, which is basically the same for the CPU. While the loop procedure is executed infinitely, as long as the power is supplied to the board and the MCU is running. Okay, so before we can turn on our LED, we must program pin 13 to work as output. We only need to do it once, so we will place it into the setup procedure. Here we go. Pin mode, 13, output. Note that Arduino uses C programming language syntax, which means that procedure parameters are put in parentheses, separated by commas, and each statement has a semicolon at the end of the line. Now, to turn on the LED, we need to write a digital 1 onto port 13. To do this, we use the digitalWrite statement. digitalWrite, open parenthesis, 13, comma, high, close parenthesis, semicolon. High means digital 1, low means digital 0. You have to use capital letters for that to work. Please note that high and low in Arduino IDE are constants. You can use 1 and 0 instead, and it'll work, but Arduino developers recommend to use high and low for compatibility among boards. We can put the LED turn-on statement either into setup or loop procedure. It doesn't matter, because running it only once will already accomplish the task. On the other hand, if we keep turning on the LED in a loop, the result will be just the same. It will stay on. So, our first sketch is ready. Now we must upload it to the board. Push this arrow, and we can see that the LED is now on. Let us replace the second parameter with low. Upload the sketch again, and now the LED is off. It's working! Wow! Are you eager to experiment? I am. What do you think is gonna happen if we put both commands into the loop procedure one after another? Will the LED flash? Let's try it. Instead, we can see the LED is now glowing, but is not flashing. Or is it? In fact, it is, but it's happening so fast our eye cannot distinguish it. For most people to be able to detect flicker, it must occur at frequencies somewhere below 100 Hz. The Arduino CPU obviously runs much faster. So, to be able to see flashing, we must use a delay command that would go between our on and off commands. Arduino IDE has a built-in delay statement whose parameter takes milliseconds. So if we put delay 500 here and delay 500 here, our LED is going to flash exactly at a frequency of 1 Hz. That's once a second. We can also change proportion of delay values if we want to end up with different on and off time duration. A piece of code that we have just written basically implements the PWM functionality, the so-called pulse width modulation. By changing the ratio of on to off duration, we can control the LED brightness. But the ATMEGA 328, in fact, can do it on hardware level. There's the analogWrite statement that does that. In my opinion, the name is a bit confusing, since this mode isn't really analog. In reality, the parameter of this command just sets PWM duty cycle and can take values from 0 to 255. Important: only pins that have the PWM sign next to them have PWM functionality. And it's different around the boards too. For Arduino Uno in particular, it's pins 3, 5, 6, 9, 10, and 11. That means you cannot use analogWrite command on pin 13, the one that has a built-in LED on. It will not set the duty cycle. So, for future experiments, let us wire an external LED to pin 11. Remember that we must use a resistor in series, of course. First, let's change pin number in our sketch and make sure the LED is working. Looks like it does. Now let us try to control it using the analogWrite statement. This program will make our LED change its brightness gradually. Here's what our sketch will look like. And we can see that LED brightness changes according to our program code. If it was your very first time running an Arduino sketch, once you get the idea of how outputs work, I'm sure you'll be delighted and spend another 5 hours playing with LEDs. Yes, you can wire any number of them to Arduino and end up with quite unusual visual lighting effects. Of course, it's possible to flash LEDs with regular TTL logic, but a microcontroller obviously allows more flexibility, simplicity, and fun. Let us now check how digital input works on Arduino. I will wire a standard button to line 13. I chose 13 because it's placed next to the ground pin, and I can use a standard 2-pin DuPont header for it. The built-in LED will also help us monitor change of level on this pin. To allow an Arduino input-output data line to work for input, we must add the pin mode 13 input statement to our setup procedure. Once the pin is set to input, we can feed logic levels to it, and the MCU will read them. But here's the problem. We need to supply both logic high and logic low, but our button can only provide a low, because it is connected to ground. Usually, one would use a pull-up resistor here. But we have a microcontroller. The ATMEGA 328 already has built-in pull-ups that saves us all the trouble and takes care of that programmatically. For the internal pull-up to activate, instead of input parameter, we must use the input pull-up. So our initialization command will be pin mode 13 input pull-up. The resistance of the internal pull-up, according to the documentation, is approximately 20K. The sketch will be very simple. We will read data from line 13 and copy it onto line 11. To perform reading, we will use the digitalRead function that takes pin number as argument and, as they say in programming, returns the pin state. Because our button is wired to 0, its logic is inverted, meaning while the button is depressed, the function will return 0, and when the button is released, the function will return logic 1. What we have just done here is substitute the entire digitalRead function along with its parameter into the parameter of the digitalWrite function, which means data from line 13 will be read and copied to line 11. If we are not happy with this logic, we can invert the data. To pull that off, all we need to do is add a single inversion symbol here. That is the exclusive OR operation, also called XOR. Amazing, huh? Now that we've learned to use Arduino for input and output, let us try to build a simple door code lock. We got 10 buttons here on our keypad, which we will wire directly to Arduino digital lines from 0 to 9. The electric magnet will be connected to line 11. The logic here is as follows. Initially, the magnet is powered and keeps the door locked. Once the correct key combination is pressed, let this be 3712 in our case, the magnet is unpowered and releases the door. It is important that all the remaining buttons must be released for this to work. Otherwise, an intruder could push all buttons at once and unpower the lock. So I have soldered the keyboard here and attached it to Arduino. Before we implement the full algorithm, let us check our keyboard using a test routine. Here's what it looks like. Here we set up mode of our digital pins. Line 11 is set to work as output, lines 0 to 9 are set to input pull-up mode. In our main loop, we read the state of each button into a separate variable and invert it. Then this data is outputted to pin 11, which is the LED. We use the logic OR operator to join input of all buttons to a single output. In programming, this symbol is used to denote the OR operation. Let us run it. So, all the buttons are working. Now we can implement our main algorithm. And the final program will look like this. The line that describes the logic of our code lock is this. Let me translate it for you. Please follow me carefully. If button 0 is released, and button 1 is depressed, and button 2 is depressed, and button 3 is depressed, and button 4 is released, and button 5 is released, and button 6 is released, and button 7 is depressed, and button 8 is released, and button 9 is released, set pin 11 to logic 0. Otherwise, set pin 11 to logic 1. After setting the electric magnet state, let us add a half-second delay command. This will protect us from something called bounce in electronics, which is defined as the non-ideal behavior of any switch, which generates multiple transitions on every input. Let us now observe how our code lock works. I am pressing the 3712, which is a correct combination, and we can see the LED is off now, which means the magnet is unpowered. Let us try pressing other buttons. Nothing happens. Let us try to press an extra button, adding it to the code. We can see the magnet is powered again. And that would be it for today. If you like this video, please give me a thumbs up and subscribe to this channel. And if you wish, you can support me by sharing this video on social media or by dropping some Bitcoin or Ether to my wallet. The links are in the description. This was Mattino. I'll see you later.